Let's consider one very common case, very important case, where we have a constant acceleration. That is the case of free fall. Near the surface of the Earth, which governs nearly all of our daily interactions, the acceleration due to gravity is constant. So the acceleration due to gravity is constant, and we give it a variable, its own variable, little g, which has a size of 9.8 meters per second squared, and it is always pointed downward. Because it's constant, we can use our kinematic equations to solve a variety of problems. So let's take one in particular. Let's establish a situation where we're dropping a ball off the top of a tall apartment complex. Okay, so we have this ball, we release it right there, it falls under the influence of gravity, so it's accelerating downward. I'm going to put the A there, and we're considering the case right before it hits. Okay. Now, I could ask a question, if I've given the height of the building, how fast is it going right before it hits the ground, or when it hits the ground? And a common concern students have is, oh, well, when it hits the ground, it's zero. It stopped. That's true, but that's not the problem that we're trying to investigate, because that is after it hits the ground, after it's interacted with the ground. There is a lot of forces happening there. It's not in free fall anymore. And so whenever we're solving these problems, we have to consider boundaries to our motion where the acceleration is constant or where it's zero. And so here, I'm going to consider the case right before or right after it leaves my hand, just barely, a nanosecond right after it leaves my hand, and then the nanosecond right before it hits the ground, so that during the entire motion from beginning to end, it is accelerating with this constant value. Okay, so with that in mind, we're going to start and do our pictorial representation and try and solve this using our kinematic equations. Okay, so first of all, let's list all of our known, our kinematic parameters, our time, position, velocities, and to do so, we need to establish a coordinate system. I'm going to choose one that may seem unconventional. I'm going to choose the release point of my ball to be 0 and choose the direction of motion to be positive downward. I'll go ahead and use the variable y to label this a one-dimensional motion straight down. Now, I could have chosen the ground measured up, which is kind of a conventional way, and that would have been fine. And your coordinate system is your choice. I'm going to choose this one because in this case all the motion is downward. The velocity is downward, the acceleration is downward, and so all of my values ought to be positive as I consider those. Okay, so with that, my coordinate system is defined that way. I'm going to now list the positions here. I've got a t0, or sorry, the variables here, t0. I've got a y0, and I have got a v0. All right, down here I've got a t1, a y1, and a v1. Okay, and then I've already listed the acceleration in between those points, and it's being constant from this point to that point. What things do I know? Okay, well, by my coordinate system, I know x0 equals 0. I could always choose my time to establish the 0 time to be when I release. What do I know about the initial velocity? What is it? Well, if it's just barely, right after I let go, it hasn't had time to speed up much. It's got essentially the absolute smallest time interval from the moment I let go. It's still 0. It was 0 in my hand, and it's still 0 at that moment. And so the speed is 0 right when it leaves my hand. Okay. The acceleration on my way down, I do know that one. That one is G. Okay. Even though it's 9.8, I'm going to leave it as a variable. That's a constant of nature that I can have on a crib sheet. I can have memorized and know that G stands for a number. Okay, and what do I know down here? Well, I don't know my time. Let's say I do know Y1, and we'll say our building is 30 meters tall. And I just realized I wrote an x0. I should have written a y0 there. Okay, I'm working in a y coordinate. Apologize for that. So I have y1 equals 30 meters, and I'm looking for v1. So I don't know it, but I am trying to find it. So I'm going to clarify. Sometimes you can get lost in these problems, wondering what am I looking for again? So I'm going to find v1. Okay, so that now is my complete pictorial representation, the setup ready to, making me ready to now use equations to solve this problem. This is so important to do this. In this particular problem, you may have a memorized answer for V1. We'll get an answer that's pretty straightforward, and you can memorize it if you want to, but the process is far more important. The process of being able to set it up, then use your equations to solve for unknown situations or complex situations is far more important than memorizing an equation for every possible scenario. Okay, so this is what we're focusing on, even though, yeah, the answer is going to come out, and you could have gotten it with a memorized equation. Okay, so I'm going to draw a little line here and say, okay, what kinematic equation should I use? We have the three. They relate time, position, velocity, and acceleration together. Let's see. I know my initial position, and I know my final position. That's good. I know my initial velocity. I'm looking for my final velocity. So I have quite a bit there. I know my acceleration. I know my initial time, but I don't know my final time. So since, even though I don't know my final velocity, I'm looking for it. I want that in my equation. I don't want T1 in my equation. And so that suggests I use the third kinematic equation, which is written this way. V1 squared equals V0 squared plus 2A y1 minus y0. Okay. Now notice I wrote the whole thing out. I didn't write out just parts of it that I already know in my mind. Again, this could, for some who have taken physics before, might be a simple problem. They want to just jump beyond that. But when we get to the complex problems, we're not going to be able to jump beyond that without making regular mistakes. And so this process is what's so important to follow. So I'll write out the entire equation as I would for any problem. This makes it very general. And then I look over here and say, well, what things can I cross off? What things are 0? So I know my y0 is 0. Okay, I know my v0 is 0. And my y1 is a positive value. My a is a positive value. And I'm looking for v1. So I can just simply take the square root now and see that this is equal to the square root of 2a y1. Okay. And I could, if I wanted to, now say it's 2g y1 to emphasize my knowledge of the special acceleration I'm working with. Okay, so that is the answer. Okay, now the physics is done for a moment here. We've finished the physics. Most of the importance in this class has been completed. There is math, and math is important. It's the language in which we speak physics. And so we can solve this by plugging in our values. V1 would be equal to 2 times 9.8 times the 30 meters. Okay, and plugging that in my calculator, I'm going to get a number that rounds to two significant figures to 24 meters per second. Okay. Now before I box that in, I need to evaluate or assess its reasonableness. 24 meters per second. Okay, this building is 30 meters tall, and I'm saying that after dropping this ball, by the time it's about to hit the ground, it's moving 24 meters per second. Is that reasonable? Okay. The value. Let's do one way. Let's say we don't have quite an intuition. We don't know what to compare it to. One way to do it is to consider moving your decimal place. What if it was 2.4? Would that be reasonable? Well, we know that the speed speeds up 9.8 meters per second every second. Okay, and this is about 30 meters. Okay, and so this is going to increase about 10 meters per second every second. If it was moving 2.4 meters by the time it got to the bottom, well, that's a lot slower than even just 9.8. So it's reasonable this might take around 3 seconds to fall. That's around 30 meters per second, which is much more similar to this. If it was 240 meters per second, well, that's moving a couple football fields every second. That's way too fast. And so this 24 seems reasonable as I consider moving the decimal place one way or the other. And then the other thing we just did is we also said, well, how fast would it be moving about every second? And 3 seconds seems to be about a reasonable fall time when dropping this ball. So I've been able to assess the reasonableness of this value and be confident that I think I did it right. You won't be able to tell, if the real answer is 22.5, you're not going to be able to say, oh, this is wrong by deduction or assessment here. But the idea is to get, did you screw up big time? Did you forget to take a square root or forget a factor of 2? Things like that. And that happens so often, so this assess is really important. Well, I've assessed the heck out of it by now, so I'm going to put my box saying I know and a little check mark for myself saying, yep, I assessed it. Now, if this was a homework problem or a test problem, you need to write that assessment out. So you need to write it out and say, this is why that number seems accurate.